All right, so we saw how to compute a linear trend using linear regression. Now we're going to work with harmonic modeling. So we're going to estimate seasonality with a harmonic model instead of using just a linear model. So we'll return to the initial time series and fit a harmonic pattern through the data. So the equation gets a little bit more complicated, and that's why, additionally to these beta 0, beta 1 values here, we're going to also have a third and a fourth values, which are our cosine and sine values, so that we can have this wave-like trend for our time series. So we'll do initially just with a one cycle per year, so we can have more than one cycle per year, so we'll have more than one wave. I guess that's probably not the right term, but 2 cycles per year, meaning you have 2 ups and downs for each year. But we're going to start with just one cycle per year, and then in the end there's one section that has a script just for changing this to more than one cycle. So first we're going to add the harmonic variable, so beta 2 and beta 3, and then we're going to fit using again the linear regression reducer. But at this time, since we have 4 different coefficients, we're going to have a 4 by 1 array image. In this section, we are also going to compute phase and amplitude of estimated harmonic model for each pixel. And this is just a schematic of what amplitude and phase would be. So usually amplitude is demonstrated from the center line of the wave until the peak. This one sort of shows you from the lowest point in the wave until the peak. So just note for that, you might see a lot of times that amplitude is just, it would be half of this measure that we have here, because it's coming from the central line. Imagine there's a central line here to the peak. And then amplitude, as it is seen here, sometimes people say 2a, which would be 2 times amplitude. Let me know if this is confusing, I can explain. And then phase is just where in the wave your point is. So it refers to, in time, in that wave, where that point is. That would be the phase. It's the location in the wave. And we're calculating this, phase and amplitude as well, because it can give us additional information to facilitate remote sensing applications. So, agricultural crops with different phenological cycles can be distinguished with phase and amplitude information, something that perhaps would not be possible with just the spectral information alone. So, like, different crops will have different phenological cycles. They have different harvest times. Sometimes they're double crop, sometimes not. So calculating phase and amplitude for that is really valuable, because with just spectral values, we're not able to probably predict, these different crops. So let's go ahead and go to checkpoint 46C. And the process will be very similar. Where I'm gonna just go ahead and go to section 4 here, all the way down. This is all that we've seen. And then here's where we start section 4. So as we've seen, we're gonna have 2 additional variables for a model. So we have the constant, we have the t, but we're also gonna add a cosine and a sine variable. So what I'm doing here is just defining a variable harmonic independence, which is just a list with the names of my variables. And then what we're going to do, we're going to actually calculate the cosine and sine for each pixel for all the images in the time series. And in order to do that, first we need to convert our time information. So our time band, we're going to select it and multiply that by 2 pi to have that in radians, because we're going to work with cosine and sine, and we're going to work with radians. We need to do this conversion. And here, so I'm just returning the image, and I'm calculating the cosine and sine for each of those pixels, and my time is in radians. And then for fitting the model, it's pretty much the same. This is exactly what we've done previously for the linear model. So we select the bands of interest. So all of these 4 bands here, constant t, cosine, and sine. And we apply the linear regression reducer. But this time, what will differ is that our harmonic independence list here will have a length of 4 instead of 2. So the resulting trend array image is going to be a 4x1 array image instead of a 2x1. And this is exactly the same thing. We're just getting rid of the residuals information, and we are flattening our coefficients band, so it turns into 2 or 4 separate bands, since we have 4 bands. So it's a 4-dimension band that turns into one image with 4 different bands. And then here, we are just fitting the values to the coefficients we have. So we're gonna have that waveform-like trend in our time series. So that's what we are doing right here, fitting the values. So we have this new values in our wave. And then we are plotting that as well. We're going to see that in a second. This is pretty much the same, just plotting the NDVI values, original, and then the fitted one after we fitted them. And then down here, we are computing phase and amplitude. So this is all geometry. So we're taking arctangent. There are, like, standard equations to do that in Google Earth Engine. So for the phase, we use this sine, arctangent of cosine. And then what we're doing here, we're scaling that to 0 and 1. So we have values in radians. So we're gonna scale that to have values from 0 to 1. And this is what we do. We have this function in Earth Engine unit scale to have results from 0 to 1. And then because it's radians, we have minus pi and pi. So that is gonna result into that scale values from 0 to 1. Same thing for amplitude. We take sine, calculate hypotenuse, cosine. Again, this is all, we should all know this from our classes. And then the only thing different here is that we are multiplying these values by 5, just because it's better for visualization. So it's not anything that we should do, is just better for visualization. So we're multiplying this resulting amplitude value by 5, just because it's easier to visualize. The image is easier to visualize. We're going to see that image in a while. And then we also compute the mean and DVI. So because we're calculating phase and amplitude, it's going to result in one image. And we are also going to get the mean and DVI, which is going to be just one image with the mean and DVI value per pixel. So we're going to calculate, that's what we're doing here, calculating a mean and DVI image. And what we're going to do here for visualization, we are actually using rule, saturation, and value for visualizing. I'm going to talk about that in a second. But for rule, we are putting the phase value, for saturation, the amplitude values, and then for the value, which is also called brightness or lightness, we're going to use the beam and DVI values. And then we're going to add this resulting image to the map. So I'm going to go ahead and run. And we're going to talk through this step by step again. So the first thing I want to show is the trend and coefficient images. So if I just clicked here over a point, and we can see actually, yeah, so this is the original linear model. But if you add these images, this one, to the map, we are actually going to see array 4 dimensions. My bad, I thought we had that added already in this code, but we don't. But it was just to show that we're going to see 4 dimensions instead of 2. And then after we feed in the harmonic model, we can see that this is what it looks like. So instead of having just a linear line for our trend, we actually have this wave-like trend for a time series. And then if I turn this image on, you can see, I'm going to turn these two off. Wait a little bit to add to the map, but all I want to say is that we're doing this hue, saturation, and value because if you were to add the image as is, the colors wouldn't make much sense. It would be just a very colorful image, and it wouldn't make much sense for us. But the way we're adding with HSV, we can actually get a sense of, we know this is water. We can get some differences between the forest pixels, the crop pixels, and the city pixels. And that's because we are using that phase amplitude and NDVI information as HSV. Let me go back here to my slide to explain that a little bit further. So this is what we are visualizing. Hue is usually the color. So for that, we have the phase, the saturation, which the amplitude is how far it is from the white color. So the more vivid the color is, that it means a higher saturation. In that case, it would be a higher amplitude value. And then for value or brightness, I'm gonna start using brightness because we're saying pixel value. So for brightness, it's just how far from the black color it is, and that's NDVI. So higher NDVI values are related to a whiter color. I know it's a little confusing, but if you want to do this exercise at home and add this image, just adding in the map and setting just RGB colors to it, you would see that it doesn't make a lot of sense. But with this HSV, we can see that like these forest areas right here have some kind of pattern with these blue, light blue colors. The water looks black, and where we have the city here is you have these gray values.